Turn off the light. Yeah, that's true. Oh, that's a real fedora.
Good evening, ladies and gentlemen. Okay, first off, can you Zoomers hear me? Thumbs up if you hear me okay. All right, terrific. Thank you. As usual, we've had some technical problem that's causing things not to go normally today. We seem to find a different one every week or every month. This time it was the HDMI cable that goes from the computer to the TV. It's a nice long cable and it didn't seem to work. But we happen to have a short cable handy. So what that means is the whole stage area is compressed up against the screen. So you Zoomers won't get as good a view, but of course we'll go full screen on the presentation. For those of you who are in the audience here and are new, the restrooms are in the back. And with that, I guess, Barb, you're gonna come up and say things. Our speaker tonight is gonna be Fran Bagenal. Barb will do more of an introduction. I will just mention that when I was a PhD student at CU, she was on my thesis committee. So I've known Fran for a very long time. And no, I didn't finish that thesis. So not because of Fran, that's a whole nother story. So Barb, why don't you go ahead and do
Yeah,
the
I'm just
introduction?
gonna stand near the mic here, so I hope the Zoomers can hear me. What I'll do is pass out, as we always do, our sky calendar, for those who are here. And I just wanted to mention about our next meeting is April 27th. And it's with Robert Zubrin on his new Mars book, and he'll be signing those and selling them here. And we may have Alan Stern another month or two after that. And what we want to do at that next meeting is any of you who are going, whether you're here in Coal Creek Canyon or going to totality to the path, we want you to share your images and photos at that next meeting. We'll probably have Robert speak first and then do some sharing of all those pictures. And if you don't have photos or images to share, we want to know what the experience was like for you. And I won't go through all of this, but I've been polling people on where they're going, and a lot of our members are going to various places on the path, and a lot of them in Texas. David Elmore, who is on here too, and will be speaking to us at the around the end about the eclipse. He's going to Mazatlan, and he's part of I think 35 telescopes that NASA and some other agencies are putting all across the path to get more information. And let's see. So I guess, yeah, we'll start with Fran, and then Leonard David will give a brief International Space Missions update. And then we also have Steve Carr here from the Denver Astronomical Society, who will be saying a few words about an event that's up at Breckenridge that they're looking for volunteers who want to come up and bring a telescope or just be there a part of it. And we'll have David Elmore talking a bit about the eclipse and eclipse glass safety. We have from David Elmore about a dozen eclipse glasses. Does anyone not have eclipse glasses here who might need them? Nope, everybody does. Okay. And we have a few other things we can hand out as well. So I'd like to introduce Fran. And Leonard and I have known her for a couple decades or so. Dewey told you about how she was on his thesis committee. And Carolyn Collins Peterson, who is one of our members, she and Mark, you were a mentor of hers many years. I guess that's about 15, 20 years ago too. And Carolyn and Mark are on a cruise that's supposed to take off from San Diego today. It may be tomorrow because the weather's kind of bad there right now. But it's a Sky and Telescope eclipse tour going for 2 weeks down to the end of Baja California to be in the eclipse path. So I'm sure we'll hear from her at the next meeting too. So just to introduce a little bit here, Fran, she got her bachelor's degree in the UK. She grew up in the UK and went to MIT for her Earth and Planetary Science degree, a doctorate degree. And she is a research scientist and professor emerita, which is the way you say it for the women, right? At CU Boulder, and co-investigator and team leader of the plasma investigations on the NASA New Horizons mission to Pluto. and the Juno mission to Jupiter. And that's what she'll be speaking on tonight. She was our speaker. We were trying to remember how many years ago, maybe 5, 6, 7, something like that. And we're just so glad to have her back again.
All right.
Okay.
Okay, great. Thank you so much. That's a great pleasure. Honored to be here. I'm hoping, because I'm a little bit shorter, I'm tilting it forward so we could see each other. I think that's all great. Good. And I see the people online. And I see Clark Chapman. Hi, Clark. Okay, so it's my great pleasure to talk to you about the Juno mission, you know, that has been in orbit for nearly 8 years. It's just extraordinary. It was supposed to only last a few months and just do a few orbits, but it's been making many orbits and doing really well. So what I'm going to do today is to go through and do a little bit about the planet, a little bit about the interior, a little bit about the atmosphere, a little bit about the moons, and so on. And at any time, if you have any questions, please do jump up and ask the questions. So let's get started and do the Jupiter 101. So it orbits the sun every 12 years. It's out at 5.2 times the distance between the Earth and the sun. And it has a mass of 318 Earth masses. So big planet, radius 11 times that of Earth. And if we spread it out, this is actually a Cassini movie image showing the latitudinal belts and zones that you're probably quite familiar with at Jupiter, with the Great Red Spot. Now, when we look at Jupiter's atmosphere, we have to realize that it's mostly this planet, hydrogen and helium, but the clouds is what you look at when you look at the planet. And the cloud deck is actually at a similar pressure to the pressure in this room that we're breathing, but the clouds are very different. The top layer is ammonia. Next layer down is ammonia hydrosulfide. So there's a mixture of ammonia with sulfur. And then we believe there's a water layer deeper down, though that's not very well constrained. Now, when we look at these ammonia clouds, we're seeing these white clouds, which is sort of what you expect from ammonia, where it sort of condenses in the same way water condenses to make white clouds. But then there's this brown stuff. What's that? We'll get to that later. Now, let's do the quick formation 101, which is to start off with the sun, which collapses from a nebula of gas out there in the galaxy. You have a sun at the center, which hot, close to the sun. So you get mostly rocks and metals making Mercury, Venus, Earth, and Mars. And then further out, you get, at some point, the frost condenses out to make snowballs. And the snowballs come together. Once you get a snowball, let's say, 20 Earth masses, you begin to pull in the hydrogen to make a gas giant planet. And so beyond this frost line, we have the gas giants with icy cores or mixtures of ice and rock and metal captured in the hydrogen gas around it. We'll come back to this topic too. This is the simplistic approach. Now, the Juno mission is sent this spacecraft out there, and the size of this spacecraft would not fit in this room. It's about a diameter of 60 feet. You can see here, you can see this human down here. Is that working? No, you're not seeing this. You do? Okay, great. And so you see the scale of this, it's huge. And the solar panels produce about 500 watts of power that powers the spacecraft. It spins every 30 seconds. So that's, it's constantly moving and spinning, keeping the antennas pointed towards the Earth and the solar panels pointed towards the sun. And then we have a whole bunch of instruments. We measure microwaves. I'll talk a lot more about that. We measure magnetic fields out here at the end of the boom. We have charged particle measurements, Jade and Jedi. We measure plasma waves with the waves instrument. We have spectrometers, infrared, that's an Italian spacecraft instrument, GRAM, infrared, UV light made at San Antonio, Texas. And then the camera, visible camera, which is amazing, just strapped on at the last minute, a little camera to take pictures in the visible light. And then we use the antenna back to Earth to measure gravity. I'll talk more about that in a minute. Now, the orbit is key for this mission because the idea was to fly over the poles and get really close to the planet. And so we fly between these really nasty radiation belts that go around Jupiter with very high fluxes of MEV electrons, which, you know, would just, within a matter of hours, would, if you were exposed as a human being, you'd be just slammed by this energetic particles. And it's also really nasty for instruments on the spacecraft. So we try to go from pole to pole, from 2 hours to go from pole to pole with this orbit. And we go under the radiation belts, above the clouds. And this was a key way of getting a measure of what's inside the planet. The problem is, because Jupiter is spinning every 10 hours, it's fatter at the equator than the poles, squished, because it's a liquid. You spin a liquid, it'll get compressed at the poles and fatter at the equator. And the net result of that is that the orbits precess, they move here from orbit 1 down to orbit 16 to 31, and you will see much later they move so the spacecraft inevitably goes through the radiation belts eventually. So that's the nature of the orbit with this 2-hour pole to pole, and then the radiation going under the radiation belts and above the clouds. Now, the spacecraft was built at Lockheed Martin, South Denver. Here's me dressed up. I kept my hands down very close to the side of my body because I didn't want to go anywhere near any equipment because I have no clue about equipment. But they let me go in and have a look. They're building the spacecraft here. This is one of the microwave antennas is going to be here. They're putting together this vault with the electronics that's going to be protected by lead and aluminum to keep it away from the radiation and so on. So that was fun. Also, you can see here they're putting together these folding solar panels that will be important for powering the spacecraft. Eventually, the thing was put together, was put on a plane, flown to the Cape, slap on the stickers, we take a selfie, and we're ready for launch. So launch was in August of 2011. We went out, we did a maneuver, we came back, got a gravity assist at Earth, and then went out to Jupiter and came out here on approach to Jupiter, arriving, and it says the 5th of July, but of course, in California, it was the 4th of July. And we had a great time. So Juno has been orbiting since 2016. The orbits are very large, started off at 53-day orbits, and has now made 60 passes over the pole. Okay, the last one was in March, earlier this month. Now, one of the goals was to try and understand what it's like inside Jupiter. And this is a textbook, literally cartoon of what it's like inside. The idea is that you have a core that's about the size of the Earth, very high density with rock and metal in the interior. And then the rest is hydrogen. But if you compress hydrogen deep down inside, you make the hydrogen metallic. It becomes electrically conducting, and that's where we think the magnetic field is. And then above that, you have gaseous hydrogen above that, with a little bit of mixture of other materials. Now, if you look at the sides here, the density shows it's very low density. And you really just need to compare it with water. One is water that I'm drinking, right? But then if you get deep, you get much higher densities, so more like rock or even more dense than iron, heavy metals deep down inside. If you look at the temperature, the surface temperature, this is in Kelvin, but it doesn't really matter a whole lot what it is. It's cold near the top, gets hotter and hotter. And once you get down to the center of Jupiter, it's several times the temperature of the surface of the sun. Now, pressure, the top is in atmospheric pressures, is about 1 at the top, as I said earlier. But then when you get deeper, it's somewhere between 100 million or 50 million times the pressure. So what do these pressures mean? Okay, so what's happening is when we talk about pressure is mass being pulled down by the gravity. And so this puts a lot of pressure. So I'm just going to stand up for those here in the audience and people at home. Tough luck, you decided to Zoom. The point is this, that my mass through my feet is a certain amount of pressure. And if I lift up 1 foot, what happens to the pressure? It's force per unit area. The area is halved. What happens to the total pressure?
You have symmetrical feet?
I do have symmetrical feet, yeah. So it's doubles, right? Because the area is halved, the same amount of force through the different area. Now, the question is, if we were to measure the pressure in this room of 1 atmospheric pressure, 1 bar, it wouldn't be the pressure through my feet of my weight. You would have to have 7 people on my shoulders, and that weight through my feet would be the equivalent to the pressure in this room. Now, we don't feel this because we're used to this, but you can check my math, and that's correct. Now, we want to go to the center of Jupiter, where we're talking something like 50 to 100 million times that pressure. What do we need to do? Not humans, but let's take elephants. And you need 1,000 elephants standing on top of each other, with the bottom elephant standing on 1 leg on a stiletto here. Okay, so I mention this just to give you the sense of how high the pressure is at the center of Jupiter. And this means that the material there doesn't behave in the way that we used to, because actually we can't reproduce these pressures in a lab on Earth. Okay, so this raises the question of what is it like inside Jupiter? And, you know, we don't really know what it's like inside Jupiter. Before we wrote the proposal for Juno, we had these cartoons that sort of suggested that there are 2 ideas. One is that you have this simple picture of a core, and then a layer of hydrogen, then a lighter layer above. Or maybe it's much more mixed up. Which is it? How do we know? Well, the way we tell with Juno is to use the radio transmission from the spacecraft back to the Earth, and we measure the Doppler shift, the slight shift in frequency associated with the spacecraft moving towards the Earth or away from the Earth, red shift or blue shift, a little bit towards, a little bit away. And this perturbation in the motion of Juno is due to the mass that's inside Jupiter, okay? So we can use this measurement to measure the distribution of mass that's inside the planet, this little difference in frequency in the transmission back to Earth. So what we've learned by measuring this with the Juno spacecraft is that no, that cartoon shown in all the textbooks is not quite right. Gee, surprise, surprise. There isn't a distinct core. It's a much fuzzier mixture with heavier elements that are partially mixed in. So when I say heavier elements, anything heavier than hydrogen, helium, so that's oxygen, carbon, nitrogen, as well as iron, magnesium, and so on and so forth as well, silica, so on and so forth. All these materials that make rocks and metals and materials, watery materials outside, they're all mixed in, these elements, with the hydrogen, helium. But instead of being a separate core, they're sort of mixed in with the outer layers.
Why not?
What?
Why didn't it fully differentiate?
Well, Okay, so this is a good question. Thank you.
You can pay me later.
So there's lots of ideas of how Jupiter formed. And I think the current thinking is that the original idea was you have this single ice layer. You make, 20 Earth masses of ice and rock. That's it. And then you pull in the hydrogen. But what if instead you have this ongoing, you start off a core, and then you start pulling in the hydrogen, then you pull in more rock and metals, and then more ice, and then more hydrogen, and it gets messy, right? And it gets mixed up in the formation process, and it doesn't settle out completely, right? Remembering those high pressures and densities deep down inside. So it's sort of maybe harder to differentiate when you have that, as also you're generating a lot of heat when you pull all this material together, banging into each other. You end up generating a lot of heat inside, which is also stirring things up inside. And so the bottom line is that it's not the simple picture of this, then that, then the other, but a more combination of things happening and it being messier inside. But remember that it's hard to do a quantitative model when you don't really know how material behaves at these temperatures and pressures deep down at the center. We haven't been able to get from NSF the money to hire 1,000 elephants and have them all stand on top of each other with the bottom one on a stiletto heel. We haven't been able to do that in the lab yet. Okay, we're working on it. So then when we look at the magnetic field is a clue because this layer outside the core, and of course this cartoon picture, you've got to think of it as being a little fuzzier now, but you have a large region, somewhere between 80 and 95% of the radius of Jupiter. It's probably actually, we think now, closer to 90 or so percent of the radius of Jupiter, where the hydrogen, instead of being molecular, where you have 2 protons and 2 electrons together, working together, they're separate. So the protons, which are positive, and the electrons, which are negatively charged, the positive and negatively charged particles can move relative to each other. And so now you can drive an electrical current. You can have motions of positive and electric and negative going in opposite directions that drives currents. And so then you can start generating a magnetic field. So what you need, the 3 ingredients for a magnetic field, is electrically conducting, which we have with this metallic hydrogen. You need to have some internal heat that turns things over. Jupiter has plenty of internal heat. It generates 2.5 times more heat from inside coming out than it gets from the sun. And then a little bit of spin. And Jupiter's got plenty of that too. Spins every 10 hours. So it has a very strong magnetic field generated in this dynamo region. And we have then a magnetic field that's inside. And actually, the Jupiter's magnetic field is not too different in geometry to first order. It's a bit like a bar magnet tilted by about 10, 11 degrees from the spin axis, except it's the opposite polarity to that of the Earth. The Earth now, remembering that the Earth's magnetic field has flipped many times over history. We've not been observing Jupiter's long enough to know whether or not it flips. Okay, but when we zoom in, which Juno is able to do because it has many passes in close to Jupiter, we can now see that the magnetic field at Jupiter is actually very asymmetric. It's much stronger in the north than the south. We don't know why, but this has an important effect on the geometry of the field and how the field affects the particles around it. And there are regions, when we look in close, this is a sort of movie of the field as we had understood it a couple of years ago. It's just getting more and more complex. And there are regions in the north where it's very strong, and you can see that red region with a lot of field coming out of the pole. And then there's actually a weaker region, which with a bit of luck you'll get to see, which is this blue spot. You can see it right now. This region here, which is this blue spot, is a weak field region, and then the polar region underneath. So it's very asymmetric when we look at it. And what we think is happening is that it's sort of like the South Atlantic anomaly that we have at Earth. And indeed, Juno is now beginning to see that this field geometry is in fact varying with time in the same way the South Atlantic anomaly has been drifting over into Argentina more recently. So we're beginning to measure this magnetic field and get a sense of how it's generated, where it's generated, and how it might be evolving a bit with time. Now, when we move up into the atmosphere, we're looking at a zone above the metallic hydrogen that's purely hydrogen and helium with some elements. We'll get to those additional materials in a minute. But let's just think a little bit about the weather. The weather is these belts and zones going one way, the other way, one way, the other way. And we'll see that in a minute. And of course, the great red spot here. So the winds, as observed, this has been observed by ground-based observations and Voyager, Galileo, and so on, as well as Juno, that we have these strong east and west winds alternating in these belts and zones in the equatorial region, spreading up towards the pole, getting weaker towards the pole. And the idea here is that we have internal heat driving convection, and you have turning over of these in these belts and zones. Now, what's important at Jupiter when we compare planetary atmospheres is to think about how Venus, Earth, and Mars, Venus, Earth, and Jupiter, Mars too, but focusing on these three, Earth we know spins every 24 hours. Venus has a very slow spin rate, and it's been slowed down by tidal forces with the sun. And you can see here that it has a very limited wind structure, quite high winds very high up, but not a lot of structure, not very many belts and zones. Jupiter, on the other hand, spins every 10 hours, and we have lots of belts and zones. Now, when we look at a movie, and we can see here the Earth above and then Jupiter below, maps of these, you can see many belts and zones, very fast winds going east and west, very regular at Jupiter. And we see belts and zones at the Earth, right? You can see the equatorial winds and the mid-Atlantic, latitudinal winds and so on. But the big difference is that not only do we have less spin of Earth, but also we have the effect of the oceans and the continents. Makes a big difference on the weather system of the Earth. So we have these similar cycloidal, we have these belts and zones, circulations in cells that we have for the Earth. But at Jupiter, because we have no continents and it spins faster, you have more of these, and they're much more regular, not broken up by continents and oceans. Now, the techniques we have on Juno to explore this is, if we look in the infrared, which is on the right, you can see, you look between the cloud layers, you can look at the hot layers underneath, and you can see some of the belts and zone structure, and you can see it's dark is where it's cold high up, and it's bright where you're looking down between the clouds deeper inside. But you're only looking at the top layer when you're looking in the infrared. To look deeper, you need to look at microwave range. You're looking at heat coming from below. And if you've got heat coming out through clouds of water, ammonia, and methane, and so on, that heat gets absorbed by the microwaves, get absorbed by water. Now, you know that microwaves are absorbed by water because that's how you heat up a cup of tea, right? You put it in a microwave oven, and the microwaves generated by the oven absorbed by the water and heated up. The same is happening in the clouds of Jupiter. The microwaves coming from the heat generated below get absorbed by the water layer as well as the ammonia and ammonia hydrosulfide layers. So this is an important clue trying to work out what's going on. And so Juno has these microwave 6 different channels on the side of the spacecraft, different wavelengths, longer wavelengths penetrating deeper. And by looking at these different wavelengths, we get a sense of the upper layers of the clouds. And then deeper down, we use gravity and magnetic fields to get a better sense of the deeper structure inside. Now, when we look at these microwaves, oops, sorry, you see this, and I'm afraid this is the only animation that I could not get to work, but if the animation worked, it's the only one of the many, you would see it varying with time. It's not the simple structure that you see with this with these microwaves, and it varies with time, orbit by orbit. And so this simple textbook picture of very simple horizontal layers is not quite so accurate. So yet again, Juno is showing the textbook's simple pictures are not quite so true. So what we're finding is illustrated in this animation here, that we have these belts and zones. We have east and west flow. We have these circles, these circular cycloidal sort of turnover of heating from below, turning things over, and driving these cells of convection with the east and west winds. The big question that we have in these multiple belts and zones is what is happening. We can only see so far with the microwave, and the gravity only gives us a hint what's happening below. So the real question then becomes, you see these cyclonic and anticyclonic motions, alternate layers, belts and zones. How deep do they go? And what stops? At what point do the winds stop? Is it because they interact with a dynamo or what? And here is a cartoon from a recent paper on this, showing maybe there's an upper cell with these belts and zones going on, but there may be a deeper cell underneath with oppositely directed convection system. So this weather system, which looks very simple and on the top layers, when you start looking at it and digging deeper, is perhaps a bit more complex underneath, with rotation playing an important role. The fact that you have multiple east and west winds and it's fairly steady shows you that the angular momentum of the planet is being tapped. Now, we did put this little, we didn't want to put a visible camera in because, you know, if you put a camera on a spacecraft, the damn geologists and atmospheric scientists, they just went, oh, we can point over here, we got to point over there, we got to look at this, we got to look at that. And the rest of us who want to make synoptic observations get our images, to our time to make observations taken away from us, from these bloody geologists. So we said no, because we're a spinning spacecraft. But we said, okay, we'll put a little camera on to take some snaps for the public. Okay. And so we got we got one from the Mars community that they wrapped up, made heavy so that it protected the radiation. We're like, okay, put it on. Okay, you can do it. Okay. Well, I have to say, it's been amazing. So the thing that's one of the cool things about this camera, apart from the fact that it is extraordinarily good, is that every single image that is taken is sent out to the public straight away. And so it's posted on this website that you can go look at. You can download the images and you can play with them and explore with them and do whatever you want, and then post them back up again. So this is citizen science at its best, and it's involved the public since day one. And I am completely blown over with how fantastic this has been. The creativity of the public has been extraordinary, but also as a source of really good science. Now, here are some examples, and this one shows you the complexity around this. This is actually not a great red spot, it's a great white spot. And you can see one of the interesting things about the rapid rotation of Jupiter and this fast east and west winds is you get these shears, wind shears that lead to this turbulence. And the one thing we've learned by looking up close with Juno is the degree of turbulence in the atmosphere is quite extraordinary. And you can see here just beautiful picture showing you these vortices that are sort of generated in this. You can imagine this wind shear driving these vortices in the atmosphere. Now you can, because they're citizen scientists that are not constrained by science, they can crank up the contrast and go, right, here's the color beam, and go all the way up. And the beauty of this, even though it's not a realistic color contrast, is you get to see this structure and you're like, whoa, look at this. This is amazing. The turbulence in this atmosphere, which, you know, amateur astronomers, citizen scientist astronomers have been making amazing movies of the atmosphere and weather of Jupiter for many, many millennia. But you don't get this close up. And this close up is really showing you this gorgeous detail. But also you could do some science, you could do some art, and the art has been fun. Like this, you've maybe seen this picture already. And many, many, many other creative things that the citizen scientists have been doing. This is as the orbit has been evolving, we've been getting closer to the northern hemisphere. And you can see here, this is for very recent, just this past month, the complexity of towards the high latitude region, northern regions, where this turbulence is just extraordinary. Again, they've exaggerated the color contrast, but it shows you the structure in gory detail. Now, when you move, remember, previous missions and all observations of the Earth is only 3-degree tilt, right? It's spin axis. So when you look from the Earth, you only see the equator. You can't see the poles. You can see towards the poles, but not the actual poles. Similarly, with spacecraft like Voyager and Galileo and Cassini and New Horizons that either flew by or even went into orbit, they were confined to the equator. They did not see the poles. And so Juno has seen the poles for the first time. And this is what we see. We see polar vortices. Now, this is a visible image. And the blue here, I think, is the really scattering that we see with the Earth's atmosphere, scattering by molecules of sunlight, preferentially in the blue, making it look blue, right? So the same physics that we have for the Earth's atmosphere. And I'll come back to why the equatorial regions are more red. But what's interesting is to look at different wavelengths at the pole. And we compare the infrared images and the visible. So the right half of this picture is invisible light. So you can see the usual picture of Jupiter, and you can see this polar region above here. But then look on the left. And again, I showed this before, where with infrared, the dark regions, which are very high up, are dark. You don't see much. The brighter regions are deeper down, where it's hotter between the white clouds. Now, when we look at the poles, this is what we see in the infrared. The North Pole, we see 1, 2, 3, 4, 5, 6, 7, 8 vortices around a central vortex. The South Pole, we see 1, 2, 3, 4, 5 around a central vortex. And this is what we have seen for the past 8 years. Hasn't changed. The North has seen these 5 and the South has seen 8. And this is a little movie showing you orbit by orbit, there are changes. And there seem to be little vortices that try to get in. And they either get gobbled up or they get spat out again. But on average, you know, when you look at these big ones, stay the 5 in the South and the 8 in the North. And why is it different North and South? Good question. How often does it change? We don't know. We've only been looking for 8 years. Who knows? Okay. So the weather system is very persistent on Jupiter. It's not like Earth, where we're trying to get a forecast for the eclipse in 11 days' time, and we're having a really hard time getting a reliable prediction. Jupiter is pretty easy to predict what you're going to see, right? Except for in the small scale where you have a lot of turbulence. So let's talk a little bit about the big feature of the atmosphere, the Great Red Spot. And here is a Voyager image taken in 1979. And Voyager 2 is in July of 1979. And they took images. But let's talk a bit about the history, because, you know, going back to Cassini and possibly earlier, this Great Red Spot has been observed and monitored by astronomers for many, many decades. And if you look at the more recent images, these are photographs rather than the sketches that the early astronomers did. But you see the Great Red Spot in these. It moves around a bit, but it's been persistent. This is the image that I remember from Voyager 1 was taken March 4th, 1979. And it was just so fantastic. And just to see something come up on the camera, on the TV where we were watching at the time, and then the next day for it to be in the New York Times is really amazing. Of course, it was only black and white in the New York Times, but it was on the front page of the New York Times, which was pretty impressive. Now, at that time of Voyager, we knew the circulation was about 6 days. We could measure that. And it was about twice the size of the Earth at that time. And it seemed to be a high pressure region with this circulation. Now, when we look at the Great Red Spot with Cassini, Caroline Porco, who was PI of the visible camera, was very concerned to try and get a calibrated color. And this was the calibrated color of Jupiter, much more muted than the Voyager colors. And this is a color of the Great Red Spot that's sort of true color, at least it's claimed to be true color. But what is the right color? And what does color mean? Okay, so this is a good question. We'll go on and on about the Great Red Spot. Why is it red? Okay, so the idea is that you have UV sunlight coming in, interacting with the outer layers, breaks up the molecules, they interact, they make bigger molecules and aerosols and so on, and this generates color. Okay, and we see this here. When you're in the mountains looking out towards Denver, you see the brown cloud, right? And that is indeed photochemical reactions between the sunlight from, UV sunlight interacting with probably pollutants, coming out of cars in Denver. Also happens in Boulder, but we don't like to admit it. So what is this chromophore thing that generates color, and how does this work? So this is what the idea is. And so the idea is that you would take UV, but with ammonia hydrosulfide, and sulfur is yellowish, so you would make a yellowish orangey cloud, right? So Bob Carlson tried this in his lab and he got lime green. Uh-oh, that can't be the explanation. So then he said, what if we add acetylene, C2H2, you make this complex hydrocarbon that combines hydrogen, carbon, and nitrogen, and guess what? It's yellow. Voila, there you are. So now, this happens to be the same pigment, by the way, that makes the yellow lines on the road, or the yellow in your inkjet printer, just by coincidence. Happens to be the same as colors the atmosphere of Jupiter. Wow. Anyway, this is what Kevin Baines calls the creme brulee model for the Great Red Spot. You have these aerosols of this mixture of stuff, hydrocarbon, the top layer, where the UV interacts, and you make this top layer of orangey stuff that accumulates over time on places like the Great Red Spot. So how much do you need? Well, I did this experiment at home, using food coloring and glass of milk. Took a pint glass and I put 1 drop, 5 drops, and 10 drops, stirred it up. And this is the amount of coloring, right? So 140 parts per million. So you got 1 drop of coloring and 140 million drops of milk. Okay, so that ratio of 1 to 140 million. Now you do 5, you've got 700 parts of color per million parts of milk, and then to the right, 1400 per million. Okay, so you get a sense of the amount of coloring using food coloring. Now, when we actually look at the chromophores on Jupiter, you only need to match the spectroscopy, you only need 61 parts per billion. So tiny, 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 tiny amounts of this chromophore, this hydrocarbon in the outer layers, makes the great red spot red. Okay, you don't need very much. Okay, so then what about the size? The time of Voyager, it was, you know, about twice the size of the Earth across. And the question is, how deep is it? Well, the answer is probably, even if it's as deep as you could possibly imagine, it's still fairly thin on a surface layer. It's still a very thin layer on the planet. Now, look at the great red spot. So this is a Hubble picture taken, I think about 15 years ago. But you can see this beautiful red spot. This is what Juno found. At least it's what the citizen scientists said. This is what Juno found. Okay, fine. You get it. What Juno found was that it was about 1.5 times. It had shrunk. Aha. And it seems to have gotten darker. Look at this beautiful picture of the great red spot with all this turbulence around it. It's just, oops, just gorgeous. Here we have images showing the flows. And these are, John Rogers is a citizen scientist. He runs the Jupiter Astronomy Club in the UK. And they're always mapping out the geography using ground-based and Hubble and Juno images to try and work out what's going on with the weather at Jupiter. But when we look at the microwave, we see that this great red spot actually goes quite deep. And this is a current sort of cartoon of what we think is happening. You have stuff rising up, it moves around, and then descends down on the sides, and you have this big weather system. Now, why there is a weather system in the southern hemisphere and it stays persistent for centuries, that's the right word, not just millennia, is not clear. Oh, I knew this was happening. There's a delay here. So it's still shrinking. If we look at perigeo by perigeo, these are all Juno images, seems to be getting slightly smaller. At the YouTube at the bottom is the link to a talk I've given on the great red spot. I've done this at the planetarium as well. There's a whole lot that we could talk about the great red spot that's kind of cool. But let me just point out that Amy Simon Miller has been mapping the size of the great red spot over time. So this is vertical, this is here, vertical axis is length. So that's how much it is across this way in number of degrees. And then this is time going back to 1880. And so you just ignore the red points for a minute. Those are the drifts around. Just the black points, you can see in terms of Earth diameters, it's like 2.5 Earth diameters, 3 Earth diameters. It's getting smaller with time. And if you extrapolate forward, it will disappear around 2080. Maybe, maybe not. Maybe it'll come back. Who knows? We'll see. This is for the next generation to find out. We don't know. Okay, so Juno is coming to the end of its mission. We've been extended from the initial 34 orbits to 76 through the end of September of 2025. We're currently here at about orbit 60, 61. We're between those two. We've been making the orbits a little shorter. They're now 32-day orbits, so more frequent and shorter. But what we're seeing is as they tick down, we're starting to cross. So they go, it goes around Jupiter this way. And so as we approach Jupiter, we're now crossing the equator closer and closer and closer. So if we zoom in, you can see we went past the orbit of Ganymede around orbit 34, Europa 43, 2 flybys of Io in 58 and 57 and 58. And eventually we will move in towards the ring region of the rings and into that nasty, nasty, nasty region of the radiation belts. So who knows if we'll actually make it all the way to 76 orbits, but that's the current hope, fingers crossed. So let me show you.
Question.
Yes.
Perigee is shrinking and it's getting more and more gray.
The apogee is shrinking. So apogee is the distance furthest away, like apogee. Furthest away is getting smaller, but the closest approach to Jupiter, the perigee or perigee, is the same. It's about 1,500 kilometers off the cloud deck. Okay, we don't want to get too close to get into the cloud deck, because then the drag would slow down and the spacecraft would get lost. So we keep it at the same height.
They have a way of keeping perigee from getting smaller and smaller and smaller.
Yes, well, there isn't enough atmospheric drag up here for it to change much, but we do orbit corrections every orbit, little orbit tweaks. Yeah.
And how do they do that?
With a firing a jet.
Oh,
There's a little bit of gas left in the jet.
A little bit left. Okay.
A little bit left, not a whole lot, just a little bit.
But 2025 is a physical restriction, not a monetary restriction.
Well,
Radiation or fuel, which one's gonna kill it first? Mining, radiation or fuel?
you know, we're taking bets every team meeting.
Okay.
And we're also taking bets on which instrument is going to die first, which is kind of a nasty thing to say, isn't it? It's horrible, but we're having fun. You know, personally, I think it's going to be radiation. Yeah, I think it's going to be the radiation. We're doing okay. We only had a few hits, but it's going to get nasty in there. Yeah, yeah. And actually, the problem with the fuel is we don't know the fuel budget very well.
They never do. It's hard.
Yeah, it's hard, right? Yeah, they don't have a good fuel gauge. Okay. Okay, so we're going to go in past, we've been past the moons. This is just to show you a little bit of Galilean moons 101. We have orbital resonance of Io, Europa, and Ganymede. Ganymede goes around once. For every twice Europa goes around, 4 times Io goes around Jupiter, and this causes a tidal heating due to this resonance, distorting the shape of the moon due to this gravitational forces between Jupiter and the neighboring moons. And the closer you are to Jupiter, the stronger the tides. And so for Io, huge tidal forces, flexes by about plus or minus 300 feet, at least that's the guess. And what's happened is over time, you think of Callisto being one of the more primitive moons, which is more or less 50-50 ice, water, and rock. And as you go inwards, more and more of the water has been evaporated, driven off by this tidal heating. You're left with an ocean underneath a layer of ice on Europa. But by the time you get to Io, there is no water left, and it is volcanic up the wazoo, the most volcanic object in our solar system. So here are just a few Juno pictures. we have this lovely picture of Ganymede. And if you look in close, you can begin to see more structure. These are higher resolution because we got in close and had a better camera than Galileo, and we had a better transmission rate as well. And so we're getting a few little shots of these moons, which are really cool. We're not revolutionizing the science because you only get a single flyby or a couple of flybys. The way in which we will learn a lot more about Ganymede will be with ESA's JUICE mission, which is due to arrive there, going to orbit around 2030s. We'll measure this magnetic field of Ganymede. It's the only moon in the solar system with its own magnetic field. It has a variety of surfaces that show a lot of geological activity, plus a bunch of impact craters. We see aurora, we see all sorts of stuff. And JUICE will go into orbit around Ganymede, like I said, in the 2030s. We move in then to Europa, and we had a flyby where we have an area that was not well observed by Galileo, and we get to see some structures. It looks like this is an area where the ice has been melted, maybe a puddle underneath, melted it up, and you have chunks of ice floating since frozen over. But this is just a little bit of a more building up the excitement for the Europa Clipper mission, which will launch this October with a bit of luck, with a bit of luck, with a bit of luck. It's being built at JPL, coming together very nicely. Hopefully it'll be launched successfully, and we'll get out to Jupiter. 2030, we'll go into orbit and then start around Jupiter and make multiple passes of Europa. Of course, trying to understand the relationship between the water in the ocean underneath and whether or not any of it gets out to the surface. And what is this brown gunk on the surface? Is this stuff that has come from below up onto the surface? We don't know. We need to go and find out. Okay, so then let's move into Io. This is a Galileo observation showing you covered in volcanoes, which are the black pieces. The yellowy red stuff is sulfur, and the white stuff is SO2 frost that comes out of these volcanoes. The SO2 frost sublimes to make an atmosphere, and much of that atmosphere is then ejected from the moon. But what's interesting is when we look at the volcanoes, even over the period of Galileo mission, we could see changes over time. We can see these big plumes of material spewing out sulfur dioxide and dust and stuff. And we saw in the infrared, there's a whole bunch of hot spots on the surface. Now with Juno, we can see these hot spots a lot better. A lot of these hot spots all over, a couple hundred at any one time, showing you this huge amount of eruption coming and going. There are changes with time. We look at different images with GRAM. We see evolution orbit by orbit. We hope to get another 15 orbits with about 8 flybys of Io, getting this sort of observation again. And this will help us try and understand what's it like inside. Where is the tidal heating dissipated? Is it very deep? Is it near the surface? And what level of activity, because we have these multiple flybys to try and get a sense to monitor the activity on Io. We do have a couple of really nice images taken by the Juno cameras. We flew by, and what was nice is that you have this terminator here. There's Jupiter shine, a little bit exaggerated on the left, but you can see this terminator with the sunshine on the right, these very high mountains, and carefully estimating them, they're something like they're about 6,000 meters, so 6 kilometers in height. So they're comparable to the Himalayas and the highest mountains in the Andes and so on. So these are big mountains that are produced by material. When you have the volcanoes, you end up disrupting the crust and having stuff sticking up into the air. So, yeah.
What's the wavelength of the infrared camera?
Oh, don't know. Sorry, I can look it up, but I don't know. My
Trying to get
apologies.
an idea how hot those.
Oh, yeah, yes. Well, we do know from ground-based observations, in fact, using Keck and other infrared and microwave observations. So ALMA down in Chile, that the lava is 3000-ish Kelvin. So it's hot. It's hot. It's like some of the hottest lava that we have here on Earth. I'm not a volcanologist, but I think that tells us it's like primitive volcanism on the Earth. So it's hot. We know that. Yeah. Yeah, sure. Good point. Here's just a hint of one of these lava flows and taken last couple of months ago. And here is a plume, suggestion of a plume on the side. You can see it just happened. Remember, the spacecraft is spinning, so you get these images. You just happen to be looking in the right direction at the right time, and you get a click, and you get an image like this. You know, we weren't aiming the spacecraft to take these pictures. And so with this, I'll just leave you with this lovely picture. And if you've got any questions, I'll happy to answer them. Thank you very much. How do you want to do this?
Who's next? What is the source of Jupiter's heat? Is it primordial?
Primordial heat, yeah. There's probably very little radioactivity because there aren't that many metals. You don't have the metals that we have inside the Earth to make the.
I was just trying to skim some stuff while you were talking, and there's a paper that says that feedback from the aurora can actually heat the inside of Jupiter.
It heats the inside.
Okay.
It can heat the upper layers of the atmosphere, and maybe, you know, it's a big planet. And when people say deep, there's deep and there's deep and there's deep and there's deep, right? So it's a little bit more than the uppermost layer, but it's still the outer thin layer of the atmosphere. Yeah.
All right, thanks.
If anybody on Zoom wants to ask a question, you can just unmute yourself and ask your question.
I've got a question about the phase diagram for hydrogen. Is that, since you said we can't produce the pressures, and have they been able to produce metallic hydrogen at this point, or is it all theoretical?
Yes, they have. So metallic hydrogen is produced at about 2.3 million bars. I think that's what it is. So 2.3, I think that's the right number. It's 2.1, 2.3 million atmosphere pressures. And yes, at Berkeley, they were able to do that with a laser and make metallic hydrogen. So we know that phase transition does happen. Yes. The problem is when you go to higher pressures and temperatures, we don't know what the equation of state is for hydrogen at those high pressures and high temperatures. And so we have to just guess using quantum mechanical models, or, you know, best guesses what that would be. It's unlikely that they're going to be able to make that even, you know, maybe at the center of a hydrogen bomb, but I'm not sure it's worth setting off a hydrogen bomb to find out.
Question here. What is your feeling about, I guess maybe this is just a yes or no, because it'd probably be too involved to get into deeply, but what we're about planet migration, for instance. We only talked briefly about that as far as saying you essentially talked about the classical form of planet formation. Okay, you think such as, for instance, I think in theory, Neptune was inside Saturn's orbit, etc.
Yeah, I think there's no question that the idea of migration of Uranus and Neptune has to happen. You can't make them where they are in the age of the solar system. At least that's the current guesses. And it makes total sense to have Uranus and Neptune made near Jupiter and Saturn, and then migrate outwards and scatter what became the Kuiper Belt, but all of that water scattered in to give water to the Earth and Mars and so on, and then scatter out stuff to make the Kuiper Belt. I think that makes total sense. The question is, did Jupiter or Saturn might also migrate inwards? And there's some argument for that, such as making a gap, you know, why there aren't larger planets between Earth and Jupiter. But I think that's still up in the air as to how that actually works and whether you need to have Jupiter moving at all. Personally, I found it really hard to find out how you would move an object as big as Jupiter.
Yeah,
Have
I
it
think
migrate.
that was originally as a result of so many hot Jupiters
Yes.
found in.
Yes, now that's
exoplanets.
different. Okay. I'm talking about our solar system. So to move our solar system in any way, move planets around. Uranus and Neptune, yes, probably not Jupiter and Saturn, though there's some debate about that. If you want to make hot Jupiters, that is, move an object the size of Jupiter and have it close to the planet, many of the exoplanets, particularly the early ones that were discovered, are indeed as big as Jupiter or bigger, closer into the star. And to do that, you do need to have a migration inwards. And I think the idea is that you have a persistent gas in the nebula. And so there's drag that brings the big Jupiters in close to the star before you clear out the gas. And I guess in our solar system, we were lucky enough that before Jupiter, Saturn started migrating inwards too far, we cleared out the gas and got rid of the drag. Okay. So it's a different situation. We did learn about migration by looking at these other planets, but luckily Jupiter has not migrated in next to the sun. But if anyone knows better than me, speak up.
Might there be a connection with the fact that a lot of those hot Jupiters are around red dwarf? So
That is beyond my capability of commenting on. Sorry.
What about the old science fiction idea that Jupiter could have ignited and be a second sun?
It doesn't have enough mass.
Too small.
Yeah, you need 20, it needs to be 20 times bigger to have the pressure high enough. I mean, it's a lot of pressure, not, 1,000 elephants on the bottom of still on a heel, but that's not enough to cause fusion. And so, no, it's not big enough.
In 2010, the aliens shrink Jupiter to make it.
Yeah, right.
I
Yeah.
found it a little bit pretty interesting that actually the pressure that you're talking about within at the core of Jupiter is actually denser than white dwarfs.
whoa.
Okay. But we don't know if it's the number, there's a factor of a few in there with uncertainty, right? So don't it's probably not 100 megabars, it's probably less, 50 or maybe a bit less. So yeah.
Okay, anything
Okay.
else?
Great.
Any Zoomers?
I think Clark's gone to sleep. Okay.
All right, well, thank you very much, Fran.
Okay.
All right, so next up will be Leonard. So let me get his presentation going here. By the way, you Zoomers at home, this is some really smooth animations. I could tell it was jerky for you guys at home, but they play beautiful in the hall.
Come on down. While they're getting set up, I just wanted to ask, will any of you be here in Coal Creek or in the Denver area for the eclipse? We're trying to do, or we will do, a event at our K-8 school and the Coal Creek Canyon Parks and Rec, who is our sponsor. They Rena Bennett did that group, and I am trying to plan an event. And Stephen, you're gonna be here. Be great if you could be there. They've got 100.
See
For
this?
medical appointment.
Oh, no, cancel those.
I'm not sure you were there, so.
Okay.
But they.
Okay,
Oh,
and yeah, they got 100 Eclipse classes, they have 75 students and then staff. And so they've got a new amphitheater. We're gonna do a little event where they can look at the partial solar eclipse, which will be 65% here. And then we're gonna take them inside the gym to see some of the coverage of the totality path.
Yeah.
So it's really exciting, and that's one of our first SkyWatcher's activities with the school, so.
We should see more of those.
We want to do more of those and probably a star party at some point for, you know, the kids. Okay.
Yeah, that sounds great.
All right, Larry, take it away.
okay. I'll make mine brief, but we've had some really, as always, some exciting things happen in the last couple weeks. First thing that happened back in March 14th of this month, we had SpaceX do the third test flight of their Starship, the huge 33 engines roaring to life to get that thing off the pad. And this takes off from Texas. And this one, Elon Musk and the SpaceX group, pretty much following the path of, test a little, fly a lot. If it fails, fix it and we'll move on. And this flight was much more successful than the first two flights. He's got another flight that may happen in the what am I writing? June, I think we're looking at June. Anyway, this flight actually had their booster take the Starship up to ignite its own engines on the Starship. So that was a big breakthrough for them. It went on a suborbital trajectory. The Starship didn't go into orbit. It wasn't supposed to be. It was a suborbital lob, and had some problems coming in and reentry, and some tiles flew off and things. And I think we're still waiting for the full analysis of what happened, but it was definitely a bigger bang for the buck for Elon Musk. It was a great flight, and like I said, he's cranking this off. Why is this important? NASA is relying on the Starship for the Artemis program to put humans back on the moon. So he's got a rapid test program to try to get this human rated eventually for his own company. But also, the NASA is waiting for this vehicle to be flight worthy and may take Artemis astronauts to the moon at some point. And so it's a work in progress, but he's making progress.
When did it land?
When did it land?
Where?
Where? It kind of re-entered in the Indian Ocean. It broke apart at high altitude, and they lost the vehicle and re-entry. And so, but again, if you're a big SpaceX fan and love this project, it was a big success for them. The one thing that people are sort of not paying attention to, and I just started, Russia has got some really interesting development going on with a new launched Cosmodrome. And they're going to fly this Angara booster. It's a heavy lift vehicle. This is the first time this particular vehicle is flown from, the name of this thing is the Voshnoy Cosmodrome. It's been in the news mainly because of embezzlement and worker problems and cost overruns and blah, blah, blah in Russia. But they are ready to, they just righted this thing up either this morning or yesterday. and it's going to fly here in a couple weeks coming up. So I'd watch this. This is very interesting to me. I think we're short-circuiting Russia out of the whole space business because of all the issues the country has at the moment. But I'm trying to keep an eye on their participation. They would like to human rate this at some point. And I think this is going to be an interesting contender. And if it fails, I think that they'll have to re-gauge themselves. But this is going to be an important flight coming up, test flight. Japan had a really interesting landing. Let's see, what did I gotta read my own notes here. It's called SLIM, for Smart Lander for Investigating Moon. Called SLIM. It did, because they actually had a engine failure. One of the nozzles blew off the thing, and it actually nosedived into the moon. It ejected some small payloads, and they're very successful. I mean, Japan became, I think, the 5th country to actually successfully soft land on the moon. So this little picture to the left there is a picture from a little toy robot that they ejected on the way down. And but it nosed in, and just the other day, surprisingly, for the second time after going through day-night cycles on the moon, it reawoke. And it's 14 days of daylight and nighttime, and it's super cold. So Japanese components are taking the hit with super cold temperatures on the moon, and reactivated, and that's the image they got from this next SLIM. And what's good about this, they actually tested some precision landing equipment, and even though it's upside down, it really came in an area exactly where they wanted, and so it's a boost for the technology that Japan has for precision landing on the moon. The one thing to watch is the Chinese. I'm always big on the Chinese because I think that's the story. They just launched a relay satellite in lunar orbit, and this thing to the left is the pre-launch picture of it. It is now in circumlunar orbit, and it's kind of sitting there waiting for the next mission that will leave in May. And it's a robotic mission to the far side of the moon. It's a return sample mission, and they need the relay satellite to be in the right position to communicate from the far side with their lander back to the Earth. So that's why that relay satellite is there. It's
Leonard, that's the second one. Do you know why they sent the second one?
I think the other one is in a different kind of orbit.
The other one, the first one's at L1 or whatever the one.
Yeah, but this one is some kind of, they call it a frozen orbit, which I don't understand yet.
So that's totally different.
Yeah, I've had a guy to explain it to me, and I can't remember what he said.
Frozen orbit is
It's very technical.
Frozen orbit's lower.
Yeah, whatever it is, they need to have this particular relay satellite, not only for this one, but their next, they've already returned samples from the near side of the moon back to the Earth several years ago. This far side mission, we've never had samples from the far side. And so this is part of their whole 4th stage of their lunar program, leading up to what they say is in 2030, they want to put humans on the moon. Anyway, they have a whole series of robotic craft, and this next flight in May is very key to their program. And so then you have Chang'e 6 and 7, and they're leading up to what they call the International Lunar Research Station on the moon. So they're, to me, that's a story to watch. As the Artemis NASA program moves to the right, somewhere in this, humans are going to go back to the moon, whether they're going to be the NASA astronauts or whoever it's going to be, or Chinese, keep an eye on that. I was just talking to the School of Mines yesterday, a couple days ago. They have a really interesting activity going on down here in Golden. They have a huge new lunar simulant facility that they're installing. It will be done probably in a couple months, but it's 100 metric tons of lunar simulant in a big facility, and they're running tests of rovers and all kinds of things that they're engaged with. But the School of Mines is doing some really active work there, and again, it's just one of those local success stories, and there are a lot of students going through there learning about working on the moon and what capability you have to actually do moon mining, taking lunar resources and converting them to other things, deep diving into permanent shadowed craters to see if there's ice in there, and what do you do with the ice when you got it. But they're really they've got a great set of programs going on down there. Just in the last few weeks, I wrote a story about people are very paranoid about the far side of the moon because of radio frequency. We got all these spacecraft going, and there's a kind of a move on at the International Telecommunications Union is involved, engaged. There's some other UN is taking a look at this. Can they coordinate lunar activities, military, civilian, whatever's going to be happening in the next few years, to try to make the moon somewhat radio quiet, to do other types of science, particularly radio telescopes, new designs about radio telescopes on the far side of the moon. But anyway, that was a big conference in Italy that just happened a couple of weeks ago, and I got to take part. I take part in everything by Zoom now. That's all I ever take part in. Anyway, very interesting development there, and then you probably hear more and more about kind of a move by various kind of astronomy groups to see if we can sequester a part of the moon to be radio quiet. In deference to Fran and Mars exploration, there was a pretty good paper that came out at the Lunar Planetary Science Conference by a good friend of mine, Pascal Lee, and a colleague at the University of Maryland on going back over some photographic data. They found an eroded volcano that nobody had seen for decades. And they made a pretty good case for what this volcano means, and whether or not it's even associated with a glacier underneath it. And what they're promoting is this area the perfect spot for a human exploration in the future. And he's got more papers coming. So I keep an eye on kind of a new evolving story about Mars, and whether or not if we put humans on Mars, where do we go? What kind of resources are going to be available?
Why?
Well, I'm not going to get into why. This is not a religious ceremony. And as always, NASA is complaining about budget cuts, so they're actually revisiting some old lunar suit ideas. And I think that's all I got. Thank you.
All righty. We have to come out this way.
Yeah, that's easier.
Okay, so.
I think we got the clips, glasses.
Next in theory, David Elmore, are you out there? You were gonna say some things about the eclipse.
I am.
Very good. Do you need to share?
I do not.
Okay,
I was glad to hear that folks in the hall have their solar viewing glasses or solar protection glasses. I like to call them that instead of using the E word because you can use them anytime the sun's out. In fact, I've been out several times in the last few weeks looking for these large spots that have come across the disk of the sun. I've learned more about how to use these. Thank goodness I didn't go blind back in 2017 or whatever. But I'd like to kind of pass along what it is I've learned of late that might be useful to you. The first thing is setting up your solar viewing glasses where inside, before you go out, set them up so that they're spaced correctly to wear. If you wear glasses, you want to fold the arms of your solar viewing glasses on the outside score. If you don't wear glasses, then on the inside score, so they fit your face better, and then put them over your glasses and use your clears. Sunglasses are not going to help you when you're looking through a 1/1000th of 1% viewer. And while you're still inside, look at the brightest light you've got in the room. And you should be able to just see it. Move your head around a little bit. If it's really obvious that there's a light bulb there, toss them, pick up another pair. So you can do this with old solar viewing glasses that you might have from the past. And it's a good idea to do this before you ever go outside and get accustomed to what it looks like. Then go outside, put them on again. You shouldn't see anything except maybe some bright glints off of very bright reflections. So you might practice to become accustomed to what that might look like. If all that's good, then next thing I've learned is putting them on. Here's the sun behind me. Put on my solar viewing glasses. Whoa! Turn around, then put your back to the sun, take them off. Another thing might be interesting is don't use your solar viewing glasses at all. Partial solar eclipses, partial phase of total solar eclipses. There are all kinds of things going on around you. Look under the trees for crescents, inverted images of the sun, and so forth. Also in the hall, Barb brought a number of these. These are from the Punch NASA mission, and they're fun 3-hole projectors. Do not look through these, but use them to project images of the sun on a surface, and you'll see triangle, circle, square images. But as you move them apart, those turn into pinhole images of what it is you're looking at, like inverted images of a crescent moon. So these things are a lot of fun. There's a great website on the bottom that has several videos for how to use these inside and outside. So I'd hope that the solar viewing glasses and the punch cards that are in the hall all go home with people. You've got family, you've got friends. And if you need any more for events that you might be attending, let Dewey or Barb know, and they can put you in contact with me. And I have additional solar viewing glasses. These are NASA, NSF, NOAA, American Astronomical Society. They're the real deal. And so I have more that I can pass out to folks. That's what I've got to say.
all right. Thank you, David. Anybody have any questions for him?
So David, I got a question. So I heard somebody say that the solar glasses have some kind of or the solar viewers have some kind of a shelf life, but that didn't seem right to me. Did you ever hear that?
I have heard that. These particular reputable manufacturers back in 2017 put an expiration date on their solar viewing glasses. This is ISO certified, and it does not have an expiration date. So I did two things. I threw away my old glasses, and with my new ones, I'm going to just test them looking at bright lights every time I use them before I go out. And in addition, I'm going to store them in a Ziploc bag so that the lenses can't get damaged.
So,
Does that help?
What equipment are you gonna be using during the eclipse?
I'm part of the Continental America Telescopic Eclipse experiment, and I have one of their standard telescopes. And they're trying to understand the solar wind kind of in a transition region where it accelerates, where it goes from laminar to turbulent flow. And in order to isolate electrons from heavier particles, it's going to be equipped with a polarization camera. And so we're going to be measuring polarization at the eclipse. And here's the back end of the telescope. And this little piece right here that actually looks more like a choking hazard is that polarization camera. It's a 12 megapixel device. It's pretty elegant. So that's what I'm doing. I'll provide a snapshot along the eclipse path about a half an hour before totality reaches Texas, and then we'll have a solid hour of observations with overlapping telescopes along the path during totality across the US.
All right. Anything else?
Thanks, David.
Thanks, David.
Thanks.
All right, so Steve, did you want to get up and say something here?
I will get up and I'll say something. Hello,
All
my
right.
name is Steve Barr, and I think I've met by far the majority of you in this room, but however, the ones that don't know me, my primary job at the Denver Astronomical Society is being the external outreach coordinator. In other words, somebody makes a request for us, and we bring telescopes out, or maybe we do presentations sometimes, or we can do sun viewing, etc. So essentially what I'm doing here and why I'm talking to you about this is because I received an interesting letter that is a little bit out of our normal range. It's at Breckenridge, Colorado. It has to do with the Dark Sky Initiative, something that we all should be concerned about, in particular as a result of the deteriorating dark skies within in Colorado itself as population grows. And I don't know how well we're going to be able to support this as a result of the distance. I know that I am going to the event, but however, one of the things I did say, I was going to spread the word with some of my friends in other clubs. So as a result, that's why I'm here, and I'm talking to you right now about it. Okay, and I think probably the best synopsis I can have of this is to just read what the initial message, and I'm just going to go back here so I can shed a little bit of additional light on my mail message that
You have a flashlight if you'd like it.
I don't need the flashlight, no. Okay, it says, my name is Danny Robbins, and I work for a nonprofit in the San Luis Valley that's spearheading a dark sky initiative. Thus, that got my attention. And I also serve as the chair of Dark Sky Colorado. I'm seeking some volunteer help at a dark sky event that Dark Sky Colorado is helping host at the Partners in the Outdoors Conference in Breckenridge this April. The event, Starry Night Soiree, is taking place at the Beaver Run Lodge in Breck on the evening of Tuesday, April 16th. It would start at approximately 7:30 and would speak of our mission and work at Dark Sky Colorado, local dark sky efforts across the state, and the importance of dark skies. Following, I would like there to be a constellation tour and some telescope viewing. I am wondering, with an amateur astronomer out of the area that will operate one telescope, and I have another. I will bring but I'm a newbie. Okay, she apparently doesn't have a great deal of experience with her telescope. I would love to have some more help to find a telescope operator and potentially someone who could lead a constellation tour. Would any of your volunteers be interested in helping? Or do you have any connections in the Breckenridge area? I just send my identical email to Ken, your public night teams coordinator, and he said refer it to outreach. So, but wasn't sure if the external outreach committee would be more appropriate. And yes, we are the external outreach committee. And one of the things, I certainly can't say that volunteers are flooding in from DAS. We have one right now, and that's yours truly. So, but however, one of the things we're lacking is somebody who can give a constellation tour. And the problem with most of the people, as with myself, I am not a myth or mythology or legends type of guy. I am just about primarily, almost exclusively, a science type of guy. So we have, and that is the case with many of us within the Denver Astronomical Society. So as a result of that, if anybody here would be interested in supporting that event, would you please talk to me later, and I can give you a card and email me, or else should you ever decide to do something to the order of this, or if you're interested ever in either joining DAS or participating in outreach, Barbara has my email address. So anyway, as I promised Danny, I am just floating that to some of the other members in some of the other clubs. So any questions about that?
I'm gonna make it come true.
Okay, well, we're going to give it a shot anyway. I don't know. We've had a little bit of a problem. For some reason, I don't understand. We've had a problem getting volunteers lately. So
As an issue, so the idea is you want to give these astronomy tours, constellation tours to the public and get support for turning off lights to
times that aren't turning off lights, or even installing lights that are a little bit more friendly.
not sodium.
Okay. Get rid of the sodium vapor lights, and which is the primary source and what many of our fielders try to filter out.
Yes.
Just about exclusively, but however, and there have been some efforts that were quite successful, such as, for instance, I know that at Mount Hamilton, for instance, in California, okay, they did manage to persuade the town of San Jose to install different lights. So as a result, Mount Hamilton is a much more viable observatory than it was, let's say, 10 or 20 years ago.
Okay,
So, okay, and that's all I have then.
thank you.
All right, thank you, good, spread the word.
So our next meeting is right here in 4 weeks, and will be Robert Segrin, and with this new book, like I mentioned before, and that book is called The New World on Mars: What We Can Create on the Red Planet. And he'll be selling the book and autographing it, like I said, personalizing it. And yeah, and then we want to get a group picture So, or do you?
Yeah, let's go ahead and do the group picture real quick before we bother with the chairs. We'll do the chairs after. Everybody just stand in front of the table. And we put up.
To keep it.
Zoomers, I think we're done with you. Good night.
It is, yeah.
Okay. Gotta get. Be in touch with John Briggs.
John Briggs. I know the name, but however.
Giants collection. down in Boise. So maybe
Yeah.
He's coordinating. Each observatory, but maybe that.
Okay,
There might be some mutual interest.
okay, John Briggs, is he what's he a member?
It's Magdalene.
Magdalene, okay. I might send you a note on that if I can. Yeah, okay.
There might be some mutual.
Can you have something like that in the background? Do you have a better slide out of your presentation? You'd rather have that or that one?
Yeah.
Very good.
I don't know your presentation. You have something? Nothing wrong with it. I just thought if you go, oh, actually, this is a particularly cool shot of Jupiter that we could have. If you wanted to step.
The advantage of this is that it has the Juno spacecraft in it.
Yeah, yeah,
Yeah.
okay, sounds good.
That's
Yeah.
If we just gather up, just get a picture of everybody who's here.
okay.
Something they already know. And so even the-
Gotta get your viewers. Put them on now.
Good idea.
Yeah. One of the.
There's two of them you wouldn't see.
No comment.
No.
One I-
Doubled up. Wow.
I could take a picture.
Filament ones. You could see the filament, very nice. You see the curl. Usually there was these.
So we'd always set up and get it, we have on a tripod and the timer and all that. And now it has like.
Can I get behind y'all taller?
There's room in the back here too.
I don't know what. Somebody has to correct my
Okay.
bill. That's all.
Okay.
That's all. All right.
No.
Shouldn't you go the other way around?
I'd like to try. No,
That's.
Yeah.
Oh, it's facing both ways.
There you go. There you go. That works.
I can't tell.
Three, two, one.
Okay, one more.
Like you can really tell in the mountain.
Must have done something wrong.
Always. You're so good. Five, three, one.
All right.
Okay.
Great.
Cheers up here.
Cheers. Cheers. Yeah, that's it.
General meetings or house and reach and.
Yeah. This spring, it happened to be